HuggingFace is a platform for machine learning and data science that provides tools for creating, deploying, and training machine learning models. It offers an open-source library of models and tools, focusing on natural language processing and computer vision. The platform promotes collaboration and user contributions, making it popular among academic researchers and small to medium-sized tech companies. Click the link to explore the machine learning models offered by HuggingFace. And check out the available datasets. HuggingFace Spaces features AI apps created by the community. Visit the HuggingFace documentation and pricing for more information. Machine learning frameworks are typically written in Python and supported by frameworks like PyTorch. HuggingFace has developed a new minimalistic machine learning framework for Rust called Candle. Candle is a Rust framework, requiring explicit typing of variables. Today, we are going to build a toy model using Candle. The reason for using Candle is twofold: learning Rust and diving deep into neural networks. This is the toy model we want to work with. The input size is 4, the hidden layer has 6 units, and the output layer has 2 units. We will not consider nonlinear activation functions. So the output of each unit is the weighted sum of inputs plus the bias. In matrix notation, the outputs of the hidden layer Y are calculated as the matrix product of the input X and the weight matrix W. The bias is ignored too. Let's begin coding. However, before that, you need to install Rust. There is ample online information available on how to install Rust on various platforms. Create a folder for the project and open a terminal in this folder. Execute the cargo init command. Add dependencies to the cargo.toml file. Modify the main.rs file as indicated. The Candle result is a type alias for the Rust enum result. The main function returns either OK or an error. The device enum allows for CPU, CUDA, or metal support. With CPU selected for this project, define an array A1 of type U32 with a size of 3. Define an array A2 with elements that are also arrays. If you're new to Rust, ChatGPT is a valuable resource for quick answers to your questions. Create tensors, T1 and T2, on the specified device, using the content and shape of arrays A1 and A2. Print the tensors. Run the program in the terminal. Change the printing format and run the program again. This time, the contents of tensors T1 and T2 are displayed. To provide more examples, import the enum type to define the types of elements allowed in tensors. Pause the video to run the additional code. Later, I will add more example files to this folder. It is helpful to use more meaningful file names. For this purpose, I renamed the current example file to create tensor. Accordingly, the cargo.toml file was modified to include the new binary name. To run the binary, you need to add 2 dashes and specify the binary name. We will learn how to perform matrix multiplication using Candle, by creating a file named tensor_matml.rs. We updated our cargo.toml file to include the binary file and updated the dependency. In the source file, we create tensors A and B. And define a tensor C as the product of tensor A and tensor B. Compile and run the code. And pause the video to understand the additional code. Before coding our toy model, we explore a program where we attempt to add two tensors with different shapes, resulting in a rest error. Broadcasting encoding involves operations on arrays of different shapes, by stretching smaller arrays to match larger arrays without copying data. This concept is used in numerical computing libraries like NumPy for element-wise operations on arrays with non-identical shapes. Pause the video to try the additional code and refer to online resources for broadcasting information. Now, we can proceed with building our toy model. After importing the required libraries, we set up some constants and define a struct named model. Within the model struct, we have two weight matrices, weight 1 and weight 2. The only function associated with the struct is forward, which computes the model's output. In the main function, we instantiate two tensors, W1 and W2, to serve as the weight matrices for our model. Subsequently, we generate some sample data for the model. Upon running the code, it should execute successfully. Feel free to adjust the batch size to 2 and rerun the code for testing purposes. In the following example, I will introduce the bias parameter and encapsulate the weight and bias parameters in a struct named layer. Each layer computes the linear output as the sum of the weighted input and the bias. The model struct now includes two fully connected layers. The model applies the rectified linear unit activation function to the output of the first layer before feeding it to the second layer. In the main function, we instantiate the first layer, the second layer, the model, and some dummy data. Lastly, we compile the model and execute the program in the terminal. The current code does not cover the training of a neural network. In the upcoming code, we will delve into this aspect. First, we import necessary structs, traits, and modules. IndexOp is a trait used for tensor slicing. This crate provides foundational components for neural nets. We establish constants that define the model's structure. A struct named DenseNet is defined. Linear is a struct similar to the previously defined layer struct, with the bias represented as a tensor within the option enum. The function linear creates an instance of linear wrapped in the result enum, taking a variable builder as input. The module trait includes a forward method that takes a single argument. I just noticed that the source code for the module trait is located in the core crate. No real data is utilized here. The function dataset generates a synthetic dataset. Each input-output pair in the model architecture comprises 10 input values and 2 output values. For illustrative purposes, we assume 64 samples are available. A transform matrix beta is used to convert X into Y. Take a moment to comprehend the code. To build a neural network, we start by creating a variable map to store named variables. The variable map is implemented as a hash map within a mutex wrapper and an arc pointer in Rust. Next, we create a variable builder and pass a reference to the variable map to it, allowing us to modify the map. The final step involves defining the neural network using the new method, which takes the variable builder as its sole argument. Before proceeding with any operations on the neural network, we examine how the variable map changes after creating the model. The all_vars method returns a vector containing all variables in the map. Upon running the program, the map is initially empty but contains 4 tensors after model creation. To better visualize the tensors, the vector is reformatted and compared to the model's architecture. The first tensor represents the weight matrix from the input layer to the hidden layer, while the fourth tensor corresponds to the weight matrix from the hidden layer to the output layer. The remaining tensors represent the biases. Now we define an optimizer, which notably receives the 2 weight matrices and bias vectors so that it can update these tensors during learning. The learning rate is increased here, although the default learning rate works well. Next, we generate the dataset using the function we defined earlier, and use 80% of the samples for training. The dataset is now split. I'm not sure if this is the best way to split the dataset. Let me know if you have a better idea. Train the model using TQDM for the progress bar. The training loop in Candle is similar to PyTorch. Compile and run the program. Let's modify the dataset and rerun the program. What happens if we add more noise to the targets?